Okay, so welcome back to another video. So today we'll be dealing with an improper integral, dealing with another arctangent of our integrand. So we have x times the inverse tangent of x divided by 1 plus x to the power 4 dx. So how will we actually come up to tackle such improper integral? This one's actually going to be a little bit of a different approach. Rather than, taking things, by brute force, we have to think things another way around. What we can do in this situation, and then I'm just going to give away the first step, is that we're actually going to break the interval up of our given integrand. You'll notice that eventually, once we reach that we'll be actually performing such a u-substitution to the point that it's actually going to be very similar of, dealing with our bounds and a little bit close to the integrand as we do that substitution. And it actually makes things a little bit easier to evaluate that for, yet again, applying more calculus techniques. I don't want to give too much because I think this one's an interesting one, so that's just the first hint you want to take away before if any of you guys want to actually evaluate this problem before I continue on with the explanation. So with that out of the way, let's actually just jump right in. So we're going to split this up. Let me call our given integral capital I. So we're actually going to first split this bound from 0 to 1 off our same integrand. And then afterwards, we're actually going to go from the rest from there. So 1 plus x to the power 4 dx. Then next is add this with the integral from 1, then all the way up to infinity of x, inverse tangent of x, and then divided by 1 plus x to the power 4 dx. So with this, now let's actually perform a u-substitution. Suppose we'll let u equals 1 over x. Then, of course, we have to plug in back for x, so I'll actually instead solve for x on its own. So therefore, this is x is going to equal to 1 divided by u. Differentiate both sides, and it would make sense to do that just so we can get the dx differential on its own to substitute. So that means dx is equal to negative 1 divided by u squared, and then du. Keep in mind, we're actually going to be doing the u-substitution for this specific integral. We're actually going to leave this to the side on its own. Okay. So with that in mind, we have our dx differential to substitute. We also have to calculate our new bounds. That means if I plug 1 for x, so that means u is going to approach, or rather, it's going to equal 1. And if I have infinities for x, so that means that's going to go towards 0. So, okay, that in mind, that means now the integral. So let me first write that again. So 1 through infinity, x inverse tangent of x, and then divided by 1 plus x to the power 4 dx. In other words, we can write this in a substitution of the same thing as yet again. So from 1, 0, then I have 1 divided by u multiplied with the inverse tangent of 1 divided by u, and then divide this by 1 plus 1 divided by u to the power 4. Then with this, we'll just substitute the dx differential, so multiply with negative 1 divided by u squared, and then du. So let's actually, of course, we can fix this up. So what I'll do here is first, let me just multiply the u to the power 4 from both the numerator and denominator such that we're not dealing with a fraction under the denominator. So that, of course, means that the denominator is just going to be just 1 plus u to the power 4. And then if we actually substitute, or rather, simplify some things here, this is actually going towards the numerator, of course. Then we have that, and don't forget that I have 0 and 1. We need to change the bounds to that, so that also excludes the negative from over there. Simplifying everything out, we'll have 0 to 1. Then we'll have u to the power, u times the inverse tangent of 1 divided by u. Then we divide this by u to the power 4 plus 1, and then du. Okay, so with that out of the way, now let's actually go back to our original integral I that we're dealing with. Let me actually switch a marker for this one. So therefore, capital I so far is that we have the integral from 0 to 1 of x, then multiplied by inverse tangent of x, then divided by 1 plus x to the power 4. This is also nice that with the new substitution that, again, we're dealing this with u, but this is actually simply just a dummy variable. So I can actually just instead replace this back to x for the new substitution that from over here. So with this, that means I have from 0 to 1 of x, then multiplied with the inverse tangent of now just 1 divided by x, and then 1 plus x to the power 4 dx. Now, just going back together and then applying the linearity again, so I have 0 to 1, and I can also factor out the x, so I have x, then multiply with inverse tangent of x, and then add this with inverse tangent of 1 divided by x, and then all this being divided by 1 plus x to the power 4, and then dx. So here's the interesting thing. So you might think, how will we actually approach something like that? And what was the point of me just factoring out the x out of both of those integrals after, going backwards with the linearity? So notice that this is actually a nice little identity dealing with the inverse arctangent identity. So this is, notice that inverse, or I'll say arctangent of x is the same thing and then add this with inverse tangent of 1 divided by x, the nice identity comes down to pi divided by 2. There's actually several proofs out there that if you want to, look this up for, the derivation of all that, that's all good, but I'm not gonna go into whole details of it. There's actually, one video I did where I went over the proof, but maybe it's kind of like old. So if you want, I'll probably just link that in the video where that proof is for you guys to view. So okay, so pi over 2, substitute that. That's still constant, so I should just factor that out outside. So I so far is pi divided by 2, multiply with the integral from 0 to 1, and so that just leaves us with x, and then divided by 1 plus x to the power 4 dx. So this kind of looks a little difficult, since you might think the next step is you probably have to do maybe a u-substitution such that, or rather we have to think of a way just so we can get rid of the x on the numerator by using u-substitution, but we're not actually going to be using the x to the power 4 for the u-substitution. Instead, notice that this is the same thing written as, so 0, 1, x. Then what I can do is, this is 1 plus, then x squared, and then square that, then dx. Then with this in mind, now u equals x squared, then dx, or du, is equal to 2x then times dx. Okay, now just divide the 2, then we have the x dx cancel itself, great. And so we have to now change our bounds, but actually not really, because if I just plug in the same thing for x, u is going to be the same bound either way. So therefore, the integral from 0 to 1, actually let me first write pi divided by 4 after I divide the 2 from both sides, then that's the constant. Pi divided by 4, multiply with integral from 0 to 1 of just 1 divided by 1 plus u squared, and then du. Now, this is obviously an easy antiderivative to solve for that. The integral is actually just arctangent. So now I is equal to pi divided by 4 multiplied by arctan. It's kind of weird. We went from inverse tangent and arctan, so it's a weird, interesting, transition of the writing notation of just u, and then evaluate this from 0 to 1. And so if you plug this back in, of course, 1 is going to equal to just pi divided by 4. Plug in 0, it's going to be 0. So therefore, I, our given integral, is just equal to pi squared divided by 16. And so therefore, that is our final answer to this improper integral. So nothing, difficult with that. You just have to think a little bit creative for how you, tackle such integrals like this. This is just one of the many strategies on dealing with, such integrals. So even though it's not exactly the pattern, but sometimes you just have to, try and hope for the best. That's terrible advice, but yeah, that's pretty cool if you ask me.